Hi ladies and gentlemen, let me welcome you to the third session on ECT 204 signals and systems. Today we discuss the elementary continuous time signals and operations. The contents of today's session are your learning outcomes, then some elementary signals like the impulse signal, the unit step signal, the sine function, the ramp signal, the exponential signal, and then we will see some elementary signal operations, and some new signals are derived from these elementary signal operations, and then the summary of understanding. So in this video you will learn some elementary continuous time signals, then you will learn to simulate them in Python, then you will learn some basic signal operations, and you will generate new signals with the help of these operations. So first is an impulse function. So impulse signal is of immense importance in signal theory. So one prominent important function is the Dirac delta function. It is defined as delta t, that is equal to infinity for t equal to 0 elsewhere. This function has unit area and finds application in electromagnetics, etc. We don't usually use the signal in the signal theory. Dirac delta function can be visualized as a shrinking rectangular pulse. Like consider a rectangular pulse of width say w and height 1 by w, so that area under it is unity. Now let me shrink this to its width to say w by 2, so that its height shoots up to 2 by w. So then you put the limit w tends to 0, so that this signal shoots up to infinity, keeping the area under it unity. Now you observe that area under this curve, this delta function, minus infinity to plus infinity, delta t dt is a 1. Now another delta function called a unit delta function or canonical delta function is of immense importance in signal theory. That is defined as delta t is 1 for t equal to 0 else. It is also called the unit impulse function. That looks like this. At t equal to 0, the function value is unity. Everywhere else it is a 0. So this function also has unit area, and you can see that integral from minus infinity to infinity, delta t dt is a 1. Another important singular function is the unit step signal, that is defined as ut is 1 for t greater than 0 and equal to 0 for t less than 0. From minus infinity to 0, the value is a 0, and for 0 to infinity, the value is a 1. And at t equal to 0, the function is not defined. Now a third function is the signum function or the sine function, that is defined as sine of t or SGN is 1 for t greater than 0 equal to minus 1 for t less than 0. Here for minus infinity to 0, the value is a minus 1, and from 0 to infinity, the value is a plus 1, and the function is not defined at t equal to 0. You can see that ut is actually half of 1 plus SGNT. That is, if I add 1 to this, from minus infinity to 0, the value will be 0, and this height will go to 2. Okay, so division by 2 becomes a unit step. So ut is half of 1 plus SGNT, or SGNT is 2 ut minus 1. And the ramp signal is defined as RT is t for t greater than 0 equal to 0 for t less than 0. Okay, this is a unit, this has a slope of unity. This is a monotonically increasing function. And the exponential signal is defined as exponential of t, that is e raised to minus alpha t ut. This is defined for positive values of t. So if alpha is positive, then it will be an exponentially decaying signal. If alpha is negative, it will be an exponentially growing signal. So this is the case with alpha equal to 2, and this is the case with alpha equal to minus 2. We will see some demo of this using Python. Here we will start with the impulse function. We will appreciate the code. Here I import the numpy module as np, and the pylab is imported for plotting purposes. And I define an impulse function as imp t, that is equal to return. It takes in a time axis t, a vector of time values, and returns the concatenated value np dot zeros lent, followed by a 1, then followed by more zeros. Okay. So initially there are lent zeros, then followed by a 1, then lent number of zeros. Then the whole array is concatenated. Okay. Here I have defined a time axis, then a t, time axis t. Then for plotting a new axis from half of len im t to half of len im t plus 1, that is taken, and we plot the im t against x, and this keeps the grid on in the GUI, and this is for showing the showing the GUI. So we will run this function and appreciate the output. Here I start an IPython 3 and run imfunc.p. Now you can see that you see an impulse function here, or an approximate impulse function for that matter. This is from, say, I defined the axis from minus 200 to 200. So from minus 200 to this 0 point, it's a 0. At 0, the value is a 1. Then after that, from 0 to 200, the value is again a 0. This serves as an impulse for most practical purposes. Now the next function is, I will see a step function. Again, these are all approximations. Here also I import numpy and pylab. Then I define a step function as an array. First I have zeros, lent number of zeros, followed by lent number of ones. Then I define a time axis and an axis for plotting. Then we plot the step function against the defined axis, and the GUI is done. A GUI is shown. So if I run this code here, here you can observe the step. The axis is defined from minus 400 to plus 400. Say from minus 400 to 0, the value is a 0. Then from 0 to 400, the value is a 1. So it approximates my unit step function. Then I have the signum function. So I will open the signum function and appreciate that. Now here I have first I have lent number of minus 1s, followed by lent number of 1s. Then I concatenate this array, and the array is returned for a t value. So t is defined as an array here. Then an axis is defined for plotting. So this sig t is plotted against x. We will run this code. It is a signum, run signum.py. So here you see that is somewhat similar to the step, except that the value from minus 200 to 0 is a minus 1, and values from 0 to 200 is a plus 1. And finally, the exponential signal. Here I have the exponential signal that takes in the value of alpha and t, and here it returns the value np.exp raised to np.exp of minus 1 into alpha into t. So this is this plot is done for alpha equal to 2 and alpha equal to minus 2, and we will appreciate that. So here I plot the exponential function. Here this is used for typesetting the LaTeX symbols in the access text, that is a label text. So we will appreciate that. I will run the exp func code. Here this is for alpha equal to 2, and this is for alpha equal to minus 2. You can see that this is an exponentially decaying function, and this is an exponentially growing function. Here you can see the LaTeX symbols plotted here, like e raised to minus alpha t plotted in LaTeX text. Here also you can see that. So this is how this is an exponentially decaying signal and this is an exponentially growing signal. And with that, all signals are done, I think. Yes. Now let me go back to my presentation. So when we see some elementary signal operations, one operation is the time reversal. So what happens is we flip the signal in time so that suppose for a given signal xt, the time reverse version y of t will be x of minus t. It is flipped around the origin. So the time reversed version of ut and sgnt are shown here. So ut was earlier, it was from 0 to infinity. Now it is flipped from minus infinity to 0. It is 1, u minus t. So sgnt is a flipped version of sgn minus t is a flipped version of sgnt. Here from minus infinity to 0 the value is a 1, and from 0 to infinity the value is a minus 1. So these are the time reversed step and sine functions. And then another operation is the time shift. For a given signal x of t, the time shifted version yt will be x t plus or minus say tau. So plus and minus sign indicate advance or delay by tau units. So ut minus tau and ut plus tau for tau equal to 5, that they are shown here. So ut minus 5, it is delayed by 5 units. So it starts at t minus 5 equal to 0. This origin is at t minus 5 equal to 0 or t equal to 5. The new origin is at t equal to 5. So this is delayed by 5 units. Here, this signal is advanced by 5 units. My ut signal is advanced by 5 units. The new origin will be at t plus 5 equal to 0 or t equal to minus 5. So this is how the signal looks like. This time advance is not a practical thing, but a delay is often seen in practical systems. So now we can combine this, that is a time reversal and shift like u minus t plus 5. If we say first it is a time reverse and then shifted. So it is essentially a time reversed signal. So it is a u minus t. So it is from minus infinity to 5. It is a plus 1. So where does the origin come? Origin comes at minus t plus 5 equal to 0 or t equal to 5. So likewise, u minus t minus 5 is a u minus t signal, but it starts at minus 5. So it is from, the signal is 1 from minus infinity to minus 5. So how do you ascertain the new origin? By making this argument equal to 0. So minus t minus 5 equal to 0 or t equal to minus 5. So many other signals can be generated by the above operation, by time shifting or by time reversal. We can generate many signals. So if you look at a sequence of time shifted impulses and add them together, we can form an impulse train or train of impulses. You can see here. This was my original delta t function. This was my original unit delta signal. Now this is a advanced. This is a delta t plus tau. And here this delta t minus tau, it is delayed by tau units. Then you can have a delta t plus 2 tau, then I can have a delta t minus 2 tau, etc. And if you add them up together, you have the signal sigma delta t minus I tau, I from minus infinity to plus infinity. It is an impulse, a train of impulses like this. This is immensely useful in sampling, etc. We will come to that. So you can see that these impulses occur at 0 tau, plus 2 tau, minus 2 tau, etc. So this spans from minus infinity to plus infinity. So this is how I generate an impulse train with by adding time shifted impulses. Now about a unit pulse signal. A unit pulse signal pt of width can be generated by subtracting a delayed unit step from the original unit step. That is, pt is ut minus tau. So graphically you can see here, this is my ut signal and this is my ut minus tau, that is delayed by tau units. When the second signal is subtracted from the first signal, I get a pulse signal of unit height that spans from 0 to tau. That is pt is ut minus tau. Now coming to the end, the summary of understanding. Here you learned some elementary continuous time signals. Then you saw the impulse function, the ramp function, the exponential function, etc. Then you appreciated the simulation in Python. Then you learned the basic signal operations. Then you learn to generate new signals with these operations. And that is the end of this presentation. Thank you all.